So welcome everybody. This is the second in our Tuesday at 2 online masterclass series. We are WasteWater Education. Although we're based in Northwest Michigan, we provide services basically nationwide and to some overseas companies as well. We perform our distance learning activities via the Blackboard Collaborate program. And move on here. Again, I will be the moderator for today. My name is Dendra Best. I'm the Executive Director for WasteWater Education. Please note that we have an ongoing commitment to service and provide access for the sight and hearing impaired. And also we recognize that several people will want to access the information on this event, and English is not their primary language. If you would like a text transcription of this event, all you have to do is email me. The disclaimer, of course, at the bottom there is that we do not endorse or recommend any one product over another. We are strictly in the education business, so the information and conclusions that are presented here are the opinions of the presenters themselves. And although we are extremely grateful to Rodney Ruskin of Geoflow for making the presentation today, this is done as an education basis. And at this point, I would like to introduce Rodney. As you see, he is the CEO of Geoflow. His contact information is there, and there's a picture of Rodney. And Rodney, at this point, I'm going to turn my microphone off and hand over to you. But please keep a note and watch on the participant window. I see at least one person there who has a couple of orange bars next to their name. That just means that their connection speed is a little slower today. As long as it's orange, it's not too much of a lag time. Just take some time letting the slides load. If you see a red bar there, please slow down and let that person catch up. And with that, Rodney, over to you.
Can everybody hear me? Is it nice and clear?
Yes, it is.
Good, thank you. Well, if you need to contact me, here are the contact points, and they will be repeated at the end. First, I'd like to thank Dendra for some of these beautiful photographs that she turned up for this presentation, and this one is particularly spectacular. Okay, virtually everything of a real technical nature and drawings of what I'm going to talk about this morning or this afternoon for most people here, you'll find on the Geoflow website at these two links. Okay, SDI, subsurface drip irrigation, is not new, and under freezing conditions it's not new. There's many very old systems that are working well and have been working well, and if it's done right, it works. However, it has to be done right. It's true of all these things, and in the case of freezing, you have a little less tolerance if you do it wrong. Okay, I'm going to talk about various subjects, starting with freezing. Then if you have high water tables, groundwater separation of mounds, coarse soils, slopes, lakeside and oceanside lots, and maintenance. Now, some of these are of course common whether you're dealing with freezing conditions or not. And incidentally, if anybody wants to ask questions or raise anything while I'm talking, please just put it up on chat, and I will either answer, if it's appropriate, I'll answer as we go, or if I've got the answer coming up anyway, then I'll just wait for the answer to come up. Okay, the first old system I'm going to talk about is the Cliff Dweller Hotel on Lake Superior. You can see the position on the map there, and this system went in, if I'm not mistaken, in 1997. That's correct, 1997. at the Best Western. It was probably Wayne Golly. I think some of the people here will probably know Wayne was responsible for it. Of course, he was the Delta representative at the time, and the University of Minnesota were managing it at the time. I presume I explore it okay. So, and that has been in, and I understand is still functioning extremely well. Okay. Now let's look at some of the design aspects that are vitally important. Okay, the critical areas are the manifold and the vacuum relief valves. These are the manifolds and these are the vacuum relief valves. These are the areas that are most likely to freeze and cause trouble. Not specifically the drip tubing, even though in this drawing it says, you know, drip tubing. Let me just get a pointer. Drip tubing should be level on contour, avoid sags. Well, sure, of course, do that. But if you get a sag in the tube and a little bit of water remains when it's switched off, and it may freeze, it could happen, but then the warm water is going to come in from both sides, from the manifold, from the supply and from the flush side, will come into the center, you know, wherever that little frozen bit of ice is. It'll be only a few inches, and it will get melted away very quickly. So, but the real issues are the manifolds and the air vacuum relief valves. From my experience, when we've been called, that is virtually always the problem. So, as I said earlier, it isn't that complex to manage that. You'll notice here that on this drawing is by Scott Wallace, who was, I think, from Wisconsin, if I'm not mistaken. Doesn't really matter, Minnesota or Wisconsin. He uses 2-inch schedule 40 PVC for all his pipelines, because he wants to be able to get a pipe warmer through. There's a device that you can pull through a pipe that will heat up pipe if by any chance, for any reason, it does get frozen or something goes wrong. So he always designs with the 2-inch. Okay. You'll notice down here, he's got a throttle valve on the flush side. So this means he's actually got continuous flush taking place, because that's just throttling back the flow. And when it's switched off, it just drains through this valve. I'm not wildly enthusiastic about continuous flush, and we're not going to have that discussion now, otherwise I need another hour. However, it does work if it's done correctly and done carefully. But again, I would rather have an electric valve there, and when the system is switched off, the electric valve opens and the system flushes at full flow instead of being throttled back. So I prefer a valve there. Now, a solenoid valve does not work very well there, because a solenoid valve, which in this case will be normally closed, takes a certain amount of pressure to keep it open, a certain amount of head pressure. So you'll have some of the water will be stuck up here when it closes down, and there's a risk of this freezing. So an electric valve is a far safer proposition than a solenoid valve. In this case, the solenoid valve is fine, because this is a normally closed valve, and it's a normally open valve. And when you switch on the pump, it will close. And now when you switch off the pump, it will open and stay open, so there's no worry about it having to stay open by means of the pressure left in the manifold, the supply line. Okay, I hope that was clear. I can't see any questions, so I presume it's okay. All right, this is the Wayne Golly's home, and as you can see down here, This is the air temperatures, and the air temperatures get down to -10 degrees centigrade, which for those who don't like centigrade is 14 degrees Fahrenheit. And you can see the water temperature, which is in the tank, in the pump tank, is fairly warm, which is to be expected because of the anaerobic and aerobic digestion that's taken place and has kept the water fairly warm. The temperature at the drip line has stayed above freezing all the way. Okay. All right. This is, again, Scott Wallace's drawing. And here he's got his drip line in the middle. He's put these bentonite seals to prevent water from seeping back into the manifold trenches. I've never seen anybody else do it other than Scott. It just seems to be a little overkill. And now he's got his manifolds, as you see, in a trench and insulated, critically insulated on both sides. Okay, you do want vegetation. Vegetate drip field with grasses to trap the snow. When you've got snow on the ground, you have far better insulation than when you don't have snow on the ground. Okay? And he talks here about drain back. The slope, as we spoke about before, must be greater than 0.5%. That's the very minimum. Of course, if the ground is completely level, this means trenching down reasonably deeply into the ground. Okay, this is the air vacuum relief. Now these freeze. So what he's done here, and if you look, he's put a plastic bucket in here. It doesn't matter, it can be a big 6-inch pipe, it can be anything. And he's dug that down to below the freezing level in the soil. So warm air will actually come up through that into the air vacuum relief valve box up here. Of course, when I say warm, it's not very warm, but it's not freezing. And here he's put a bag, a porous bag with a fabric bag with some type of closed cell insulation, or styrene foam or something chipped up, and to keep it warm around, and he's insulated it all the way around the sides and put insulation across here to keep the cold air from coming up around. This is critical. If the air vacuum relief valve freezes, the manifold will not drain. I see David's asking why a valve rather than a drain back orifice. Why the air vacuum relief valve? Is that the question? If there's an air vacuum relief valve, because it lets air out as well as letting air back in, and if you had an orifice, when you switch the water pressure on, it would just flow out. You'd have water pumping out, the sewage will be pumping out all over the all over this area here. And I'm not sure if that's the correct, if I've answered the right question. If not, the question was about a drain back to the pump. So you went back to the slide. Here, I think this is the one, and here you're saying, why not an orifice? A drain back orifice. Well, if you have an orifice there, when you switch on the pump, the water will be, some of the pressure of the pump will be squirting water down here all the time. And I mean, it could be done. There's no particular reason. The same as they use the throttle valve here, they could use the throttle valve there and waste a little bit of energy. It's certainly practical. Again, this is, in many ways, this is a cost issue. And generally under freezing conditions, I wouldn't recommend trying to save money. But certainly I know, particularly in this present economy, and we're probably all suffering the same thing, the competition in the marketplace has got very, very aggressive on price. Okay. These are the basic rules. Supply and return mains must be insulated, as we discussed. Supply and return mains must be sloped back to the pump to provide positive drainage. The supply and return lines must be lower than the emitter drip line to prevent flooding of the drip lines from the manifold after the pump is off. By that, that means that the manifolds must be lower than the lowest dripper in the field. The highest point of the manifold must be lower than the lowest dripper in the field, so that we're quite sure that the drip line will 100% of the drip line will drain. Okay. Beware of slow drain back. Okay, a system that takes more than 15 minutes to drain back may freeze, because of course this is fairly obvious. So when you're checking the system, make sure that your drain back is reasonably rapid, which of course is why I objected to the design with the open drain backs rather than solenoid valves or electrical valves. Okay, we have to be aware of high water tables. If the water table rises above the drip line and freezes, well, I'm afraid the drip system isn't going to work. Drip will work in frozen soil. Frozen soil conducts water, but ice does not conduct water. So, okay. Beware of restrictive horizons. Clay, rocks, sandstone, siltstone, ironstone, different soil formations. Even if you have a low percolating soil on top of, say, sand, when the water goes down and hits that sand layer, it will flow along the sand layer and take time before it will break through the sand layer and go down. Okay. I see David's asked another question. Don't you need to prevent drip lines from draining into supply and drain manifolds? Now, I think you want the drip lines to drain into the supply and drain manifolds, and so everything empties rapidly. If you're thinking of the vacuum, as long as the height between the drip line and the manifolds is reasonable. I mean, if you had 10 feet, of course, you could set up a vacuum, but usually it's only 2 or 3 feet. That degree of vacuum should not cause any damage to the dripper.
Rodney, can I interrupt just one second? Dan Wickham has a chat open, but I don't think he's sent it yet. Dan, if you have a chat that you need to send, just click the return button. Up to you, Rodney.
Okay. All right. Now, mounds, I mean, of course, are widely used. Sand mounds in one form or the other. I'm not enthusiastic about them because, again, typically they will break out somewhere at the bottom of the mound unless the soil underneath has got the ability to take 100% of the flow that's being applied to the mound, which usually makes the mounds very, very large, and typically this is not done. However, they do work in the sense that they act as very good treatment, and this is a very interesting mound that some of you have probably seen before. This was, well, I don't know if he originated it, but he popularized it in Washington. It is a very shallow sand mound, and he uses drip line to feed the sand mound. And in this case, he's got 500 feet with 6-inch spacing, and that means he's got 1,000 drippers on the mound. That means the biological load, this is septic tank effluent, the biological load per dripper is very, very small, and the sand around it has got enough air to treat it very, very rapidly and very, very efficiently. And as you can see, there's monitoring wells. In the end, that water ends up in the wetland on the top right-hand corner, but the monitoring wells have shown extremely good results, and they are pretty well accepted as a standard in Washington today. Okay, let's look at some soils. This is one of the worst soils I've seen. This is the city of Wairika in California. It's a little over 1 million gallons a day. City effluent. The soil came from the washing for gold, the panning for gold in the Wairika Creek, and the gold miners threw all the junk and all the stuff up on the side of the banks, and this is what we were given for the wastewater disposal. I'm happy to say the creek is monitored above and below the drain field with no sign of deterioration caused by the drain field. Okay. Soil, of course, is a critical aspect in this discussion, and this is true for all subsurface strip disposal. Soil is the critical issue. I'm not going to attempt to teach anybody, particularly the particular audience I've got now, about soils, but let me just stress that that is the critical issue. And this table, which is from Jerry Tyler, and I believe is the Wisconsin standards, is a pretty good guideline in terms of what soils, what application rates you can use with different soils. You'll notice that the secondary treated BOD less than 30 milligrams a litre, he applies much lower loading rates, much higher load. What's going on here? Gallons per day per square foot. There's something wrong with this table. And I took it literally off a greater, I'm terribly sorry, I mean I can't read my own, greater than 30 milligrams, that is septic tank effluent. He applies 0.8 here, while with less than 30 milligrams secondary effluent, he's got 1.6 milligrams per litre per day, and as you can see down, he applies much more water for secondary treated effluent. However, I look at these as guidelines because it's very, very difficult to really assess this, and there isn't a cut-off point. There's the 29 milligrams you can use the one, and the 31 milligrams per litre you can use the other. So you do need to apply some good soil science and some good intelligence to the. So when it comes on the question of septic versus secondary effluent, the first issue is there's a hydraulic load, which applies pretty well with secondary effluent. With the BODs are less than 30 milligrams a litre, it's the hydraulic load, the ability of the soil to carry the water away that counts. When the BOD starts getting up in the range of 100 milligrams a litre, which then there's a very good chance that the soil will not be able to handle the biological load, and in which case then you need a larger area, and I would say more drippers, in order to handle the biological load and to divide the biological load with more drippers into more points. So I must stress that when you're handling a situation where you've got difficult soils or you've got high BODs, the whole thing is the soils, and please call in a competent soil scientist, unless you fill that category yourself, to advise you, because this is the critical issue of all subsurface strip systems. And most failures I see, other than the freezing ones, as I explained before, are because of inadequate soil science. Okay, slopes. This is a slope in Yosemite West. It's a housing development of about 50 or 60 houses that goes out to this a treatment plant and to this drain field. As you can see, the trenches were dug by hand. It is very, very steep. If I remember correctly, and I've got a note somewhere, I might have it on the next page, but the system's been in at least 6 or 7 years, or maybe more. And I was there just this recent winter, and I wanted to go out to have a look at the system, and everything, I couldn't get through, even in my Jeep. Everything was covered with 4 foot of snow, and I never got there. But yeah. And just to show that installing doesn't have to be quite as difficult as that, this is a golf course in New Zealand, where nice, easy installation, just roll it out. Okay. This is, to my knowledge, the most southern system we've got. The latitude is 46.5 degrees centigrade. It's 78,000 gallons per day. Very miserable soil, pea gravel soil. And it was installed in May 1998, and it's still operating. Woodward Clyde, who designed it, was bought out by URS, and if anybody wants to talk to him, I can introduce you to the engineer that designed it in '98, who is still working for URS. And that's how I know it's still working, as he told me. And just so you know how south I'm talking about, this is the bottom end of New Zealand down here, and this is where it is. And this is the Arctic. This is the southern Arctic ice. So you can see we are low, and it is cold. I've been there once. The wind was howling, and I don't want to go there again. Okay, and here it is again, this way to the South Pole. Okay, this is just out of interest, this is the system, dual pumps, and the filter is very similar to the Geovac. It's a stainless steel screen filter that gets cleaned out with a vac cleaning it around. And now we'll change to the north, and this is one of our more northern systems, Kamloops in British Columbia. This was designed and installed by Ian Ralston, and as you can see, the temperatures went down to minus 20 degrees C, which is minus 4 degrees Fahrenheit, and it had very little snow. And when you got very little snow, that's when you're at the most risk, and Ian reported that there were no freezing issues on the system. Ian is expert in installing in British Columbia on freezing systems, as one would expect. This is Ian's Headworks, which was used on that system. And you notice there's electric motorized bore valves here, both on both sides, both on the supply and on the flush sides of the supplying the manifolds. Now these are not submersible. They're electrical. If you submerge them, you'll be in trouble. So you've got to make sure that they are above the water level, and of course we have to be below the drain field, so this might not be possible in some circumstances. But and the rest is very conventional. I think everybody else in the audience probably knows the rest of the system. But this is, I far prefer these motorized valves, at least on the flush side. I don't think, earlier as I said, I don't think it's essentially necessary on the supply side. where it's a normally open valve, but when you're dealing with a normally closed valve, it is not going to operate correctly under freezing conditions and will leave a certain foothead of water in the return manifold. Okay, we'll now talk about some coastal systems, because again, there's a lot being done around the Great Lakes and coastal areas. This is Angel Island in San Francisco. There at the back, that's the Golden Gate Bridge, this usual cloud. Until they put this system in, they used to take the sewage off the island by tanker to a treatment plant on shore. And this, of course, was very expensive. There was an old treatment plant on the island that had originally been operating and dumping into the bay. And of course, that was stopped. And then they moved to the tanker, and then finally they turned to a subsurface strip system. This is a beautiful home on Carmel Highlands in California, where you can see it's right on the sea, and the drain field is right here. You can see the drain field here, and here's the ocean down here, and the distance is adequate. If anything does get down there, it's going to be clean, but in California, nothing much should get down there. And this is a single-family mansion in Malibu, where again, Malibu has no central sewage system whatsoever. Everything in Malibu is on some type of septic tank, treatment unit, and some type of drain field. Okay, maintenance. Maintenance is much the same as for any system, whether it's freezing or not. First of all, obviously, check your filter. Remove the filter cartridge, whether it's a disc or whether it's a screen, clean it, and replace it. A lot of people on small systems carry clean filter cartridges with them and just put in a clean one and take the dirty one back to the shop to clean. Manually flush the field. It's, just make sure, do a manual flush and make sure that everything's out, and just look at the flush water and see that it's clean. Okay, get the system running and take your pressure readings. Now, the air vacuum relief valves have all got Schrader valves on them. So you can go out into the field and take pressure readings on the Schrader valves located on the vacuum vents and compare them to your original readings, which of course you should have recorded. If you've got a flow meter, of course you can check that the flows are as designed. Some people will use a stopwatch and measure the speed at which the water drops in the pump tank, but I don't know too many people who really do that. But if you have any doubts and are worried about what's happening, that can be done. Okay. Make sure your air vacuum release valves are seating properly. Okay. I would say take it apart. I would be on pressing it down to flush out any debris, which does more or less work. Take it apart. It's easy enough. It unscrews and clean it up and put it back in again. Okay. Make sure your controller is back to auto before you're finished. When you're finished, run the field. Inspect it for wet spots. Okay. If there's any excessive wet spots, which could be caused by leaks or animal damage, repair. Okay. Once a year, or at least once a year, clean all valves and vents by taking them apart. Okay. Here I am at Ephesus with a 2,000-year-old toilet with running water. And I'm told that there are systems with running water even older than this one. Anyway, this was the one that I happened to be visiting. And I did try and follow the drain to see where it went, but this is a restored road, and I just wasn't able to. I quite quickly got lost and couldn't find the field where it was going to. But Okay, well, this is the Geoflow site, and here again are my contacts if you've got any questions or anything further to discuss. Okay, and I think I will pass over to Dendra.
Yep. Thank you, Rodney. Would you turn your microphone off for me, please? Thank you. I see that Kevin has a chat. I see that Kevin has a chat window open, and I'm not sure if there's a question coming in. Rodney, would you turn your microphone off for me? Yeah.
I presume it's now off.
No, it's still on.
What?
Yeah, just click the talk button.
I did. I'll try again.
Ah, there you go. Thank you. Just would like to mention to individuals who are on this call and for anyone hearing the recording, and yes, Kevin, we'll get to your question just 1 second, that in September the 11th, 12th, and 13th, Rodney is actually doing a 3-part regulator training workshop for us that we will be advertising. Is particularly for public health officials, but we're also opening it up to installers and engineers on how to review a design, how to write a permit, and how to evaluate the O&M plan for installing a subsurface drip system. Before I get to my closing slides here, Rodney, Kevin has a question in the chat window. It says, I have always recommended that chlorine not be used as a disinfectant with drip. In California, they are quite adamant that a chlorine residual be left. At what chlorine level is the plastic impacted? I'm going to turn my mic off so that you get yours without any echo. Go ahead, Rodney.
Okay, that seems to be working. Okay, first of all, I absolutely agree with you. You don't want to use chlorine. Not because it will cause any damage to the drip system. There's no problem. There's polyethylene. It can take as much chlorine as you could possibly ever put in. I don't like chlorine because it kills the bacteria in the soil, and the bacteria in the soil are our friends. And we don't need it. We absolutely don't need it. When you say in California, they're adamant that chlorine residual be left. Now, I don't know who you're talking to in California or which county you're talking to. I think there's 51 counties. Everyone has their own health department, and you might find someone amongst those 51 counties that has insisted that you do that. San Diego, all right, I don't know who's in San Diego, but when we're finished, please put me in touch with the person in San Diego that you're dealing with, and I'll try and persuade them otherwise. Because to say it's a county by county issue, and as you know, I live in California, and frankly, we don't generally. That is not generally a requirement, but it isn't a state rule. It's a county regulator. So I'll be happy to interfere. But the plastic is, you don't need to worry about it. And I'll say, if they insist you have chlorine, then put in the tablets and then forget to, dispense and then forget to put the tablets in. The drip, Kathy Beer asked, if you cannot use chlorine, what do you use for overgrowth in the emitter lines? Well, it depends whose product you're using, and I'm not meant to be marketing here. The drip line that I sell has got a turquoise inner liner, and that turquoise inner liner contains an antibacterial. The EPA doesn't allow me to call it a bactericide. It's an antibacterial, which is tributyl tinmaleate. And the bacteria will not stick to it. And if a bacter or whatever a bacteria is sticks to it, and it will immediately die. That bactericide is in the emitter as well. And we just don't have a biological growth problem. And but if you do, of course, you can give it a shot of chlorine. If you have something go disastrously wrong, The antibacterial does not treat the water in the pipe. It is protecting the pipe and protecting the dripper. So let's say you have a situation that somebody switches off a system and goes away for a few months, and the system is left full, which of course it shouldn't be done under freezing conditions, or nearly full. And you have a huge amount of biological growth occurring in the water, even though it's not sticking to the walls. And you have trouble flushing it out, then I suggest either using acid or chlorine and pumping it out. But that should be a one-time occasion. In my experience, it's very, very rare.
Okay, Rodney, let me close out the session, and we will leave the session open for those who want to carry on. So, Rodney, turn your mic off for me, please. Thank you. We just have a couple of closing slides then, and I'm going to stop the recording, and I'm going to open it up for open discussion. If there are other issues that haven't been addressed here, do feel free to stay online and join the conversation. We have a couple of closing slides, as I said. This one should resonate with everyone who's on the session today. The reason we are in this business is that we are all acutely aware that we live on a very finite, special blue marble floating in space. The reason we're actually here, breathing, talking, having intelligent conversations is because a majority of our bodies are composed of water, and that all the water that is on this planet has been used and reused and recycled and will be reused pretty much as long as there are people alive to realize that we're doing it. We usually explain that we are not in the wastewater business. We are in the clean water business. None of us set out to generate water that is filthy or is wasted. It's that we are all devoted, we are all passionate about providing and retaining clean water resources. Again, this is our closing information. This is our contact information. And we are at Post Office Box 792. We are based in Traverse City, Michigan. But as you see by attending the session today, we live and operate in the virtual world. We work amongst 7 regional health departments, so having a physical office space would be a tremendous waste of resources. We prefer to use the internet for all it is worth. You will find us on Facebook, Twitter, and LinkedIn. And this session today is being recorded for posting to our YouTube nonprofit channel. And you will notice here that we use the logo that EPA generated several years ago, but still is as relevant today as it was then, that clean water really does start at home. We preach the connectivity of all water use and all water resources. That being said, I would like to thank Rodney Ruskin of Geoflow for today's presentation, and a reminder that if you are a member of our listserv, you will receive information about the September event. That's a 3-part course that we're doing specifically geared towards subsurface drip systems for regulators. Thank you, everybody, and goodbye. But if you wish to stay on the call for discussion, wait for the recording to stop, please.